Hi everyone, in today's video we're going to go over a CC bond forming reaction called the Suzuki Coupling reaction. It's my hope that by the end of this video you'll be able to identify the reagents used in Suzuki couplings. You would also be able to identify the substrate scope of Suzuki couplings. You'll be able to explain why we incorporate a base in Suzuki couplings. You'd be able to draw out the intermediate structures in the catalytic cycle for Suzuki couplings. And then lastly, you'd be able to do a comparative analysis of Suzuki couplings compared to Stille couplings and figure out the advantages and disadvantages of using either of these coupling strategies for CC bond formation. So the CC bond forming reaction is an organometallic reaction that involves the use of an organoboron, which then reacts with an organohalide in the presence of your palladium zero catalyst. This is the same one we use in the Stille coupling, but now we also incorporate a base, an ethoxide base in this case, but it could be any kind of alkoxide base. You would end up with the coupling product where the two R groups from your organoboron and your organohalide form a CC bond to form its own longer chain, followed by side products including a boronic ester as well as a sodium halide in this case because sodium was used as your counterion to bring in your base. Okay, so note here that the base actually ends up on the boron and the halide from the organohalide ends up at least interacting in ionic interaction with your sodium. So we will now explain each component of our Suzuki coupling reaction. We will start with the organoboron compound. The organoboron compound could be an organoborane. With the borane, what we just mean is that the R groups coming out of the boron that are highlighted in yellow are alkyl chains. It could be a boronic ester, and all that means is that the groups coming out from that yellow highlighted spots on the boron are OR groups, so oxygens bonded to a carbon framework, and that's called a boronic ester. Or your organoboron compound could be a boronic acid, and in this case, those yellow highlighted groups are OH groups, and that's what we call a boronic acid. And so any of these three combinations of organoboron compounds could serve as your Suzuki coupling reagent. And there's a wide variety of these groups that we can use on the boron. So next we focus on the R group, so the group that we're actually going to couple in this reaction for our organoboron species. The R group can be an aryl group, so any of your phenyl rings, it could be substituted phenyl rings, it really doesn't matter. Those groups can absolutely transfer and be incorporated in Suzuki couplings. It could be a vinyl group, so vinyl group. So these are your boron that is directly bonded to a vinyl carbon, and then the rest of the chain can be whatever you want. And so those groups can end up being incorporated in Suzuki couplings. It could also be your allyl groups. So these are your sp3 hybridized carbons that are one carbon away from a vinyl group. And so those allylic groups can certainly be incorporated in your organoboron compound and be used in Suzuki couplings. What is also fascinating and actually fairly powerful for Suzuki couplings is that you can actually do Suzuki couplings with completely sp3 hybridized carbons. So alkyl groups can serve as coupling partners. And this is actually a difference between the Suzuki that we're learning in this video and our Stille coupling that it was in the previous video, where we could not use alkyl groups in those coupling reactions. So now let's move over to the organohalide. I'm going to actually put a quotation mark around halide because as we've seen in Stille couplings, we can substitute halide for a good leaving group. So your X in your organohalide coupling partner is most commonly bromide, iodide, or a triflate leaving group. We don't really use chlorides as much because they actually tend to not be as efficient as the bromide, iodide, or the triflate. And in fact, most times you would actually see this reaction with the triflate because that is an especially good leaving group. When you think about the base that gets formed in this, is you have a really, really stabilized base. because of all those resonance forms that you can draw in addition to the induction from the CF3 group. Now for the R group on the organohalide, so that's R prime, we are limited to aryl groups, just like your R group that could be on your boron, and vinyl groups. But those are the only two, so we can't use alkyl groups or allylic groups on the organohalide. So now let's focus on how we actually can prepare our organoboron reagents for our Suzuki coupling. Our organoboron reagent can be prepared by taking a terminal alkyne, such as the one I'm showing here, and performing a hydroboration reaction on the terminal alkyne. Recall that a hydroboration reaction is an anti-Markovnikov reaction where the boron ends up on the less substituted side of the alkyne and the hydrogen or the hydride group on the boron ends up on the more substituted side of the alkyne. And so in the hydroboration step with this particular borane, this is a very popular borane called Catalytic. The product of this particular reaction looks like this. So now you have an organoboron species with a vinyl group connected directly to the boron. You can also use a bulkier version of your organoborane to do your hydroboration reaction. So this is the 9BBN reagent. And similarly, you form your organoboron compound, your reagent that you can then use in your Suzuki coupling. You can also do the exact same set of reactions, this time with an alkene as opposed to an alkyne. If you want to form a more saturated organoboron compound for your Suzuki coupling, it's the same reaction. It's a hydroboration with these boranes, and you would end up with your alkyl borane compounds as the product of this particular reaction. You can also form an aroborane, but this time you have to really start from your organolithium species. You can also use a Grignard, the organomagnesium as well for this reaction. But in any case, as an example, use an organolithium, which is a phenyl or arorane connected directly to your lithium species. You treat that with your trimethyl borate species. And here is a common way you would see this particular species written. So it's a trimethyl borate species. You would end up with a displacement where that aryl group actually ends up on the boron species, and then one of your methoxy groups on your trimethyl borate now coordinates or is in an ionic interaction with the lithium. Okay, so we've seen how to essentially make a vinyl borane, an aryl borane, as well as an alkyl borane. And now we can use our species in the Suzuki coupling reaction. So now let's dive into the mechanistic steps for Suzuki coupling. And for this entire exercise, we're going to focus on one example of a Suzuki coupling where we take an organoboron compound with a phenyl group and then our vinyl iodide, and we treat that with our palladium zero catalyst and our sodium ethoxide base. Doing so, we essentially produce styrene as our CC bond forming product, in addition to our side product, which is our boronic ester, as well as sodium iodide as our inorganic byproducts of this reaction. So while the intricate curved arrow mechanisms might differ from states to states and from context to context, there are 4 generally accepted mechanistic steps for Suzuki coupling reactions. The first is an oxidative addition step. The second is a displacement step. The third is a transmetallation step. And then the fourth is your reductive elimination step. And so we're going to go through all 4, step one by one, and then we would put it all together into a catalytic cycle. So let's begin with our oxidative addition. In our oxidative addition step, our vinyl iodide, in this particular case, reacts with your palladium zero catalyst. And as we mentioned before in previous videos, we're going to ignore the nature of the ligands that are around the palladium zero for now, because they can come on and off the palladium center, and you can have different types of ligands sort of attached there. But it's a palladium zero catalyst that interacts with our vinyl iodide. And in this step, your vinyl iodide cleaves and then latches on and attaches to the palladium center, which means that once again, as such, we have added two X-type ligands onto that palladium center, which means that we've increased the oxidation state of this palladium species by 2, and hence why we call it an oxidative addition step. And now we are at our displacement step. So this is our oxidative addition intermediate. It contains both our vinyl group and the iodide that was on the vinyl iodide onto the same palladium. And so for Suzuki reaction, there's sort of a step that happens before the transmetallation. And this is really because our boron is not as good as of a transmetallating partner as, let's say, our organostanane in our Stille coupling. And so we need a little bit of oomph around this palladium center to then facilitate the transmetallation step. So the reason why we incorporate sodium ethoxide to this particular reaction flask is that sodium ethoxide or any alkoxide or hydroxide base can actually displace that iodide from the palladium center. And watching very closely our color coordinated species here, we see that in this case our ethoxide is now latching onto the palladium, so this is bound to the palladium, and now our iodide is essentially in solution with your sodium stabilizing it. So this is why we call it the displacement step. We're especially just displacing the iodide from the palladium center and into the solution. Please note that sodium is a counterion. It doesn't really form really strong covalent type bonds. This is really just an ionic interaction that stabilizes the iodide that is in the flask. Hence why it's called a displacement. And now once the palladium 2 species has undergone displacement, it's now essentially primed for transmetallation. And we're going to see why this species is particularly good with transmetallating with our organoboron compound. Okay, so here is our organoboron compound that we're going to go through a transmetallation with. So one thing to remember here is that boron is sp2 hybridized technically, and boron has a really strong affinity to oxygens. We can see even in this particular scenario, boron is bound to 2 methoxy groups. As such, there is a strong affinity for our organoboron compound to actually form a bond to the ethoxide group that is already bound to the palladium. And notice that we now form this Zwitter ionic species where our oxygen on our ethoxide gains a positive charge, and the boron that is now bound to that ethoxide gains a negative charge. This complex actually starts to push this reaction in such a way that the phenyl group that I'm highlighting in blue is more likely to now transmetallate or transfer from the boron, we're calling boron a metallic center, from the boron metallic center to the palladium metallic center. And likewise, because boron has a strong affinity to the oxygen, your ethoxide group that was in palladium now has a stronger affinity towards forming a bond to the boron over the palladium. So this is an interesting way in which we are taking advantage of the inherent affinity of boron to oxygen groups to force or to facilitate this transmetallation step. And so a product of this reaction ends up being this palladium 2 complex. Now, notice once again, the phenyl has now transferred to the palladium. So now we have both the phenyl group and our vinyl group attached to the same palladium 2 complex. They are still both X-type ligands, and so the palladium remains in the same oxidation state as where you started with. Likewise, we have now formed this trialkyl borate species as our inorganic byproduct of this reaction. All right, so now that we're done with the transmetallation, and now we have both groups that we want to couple onto the same palladium center, we can now do our reductive elimination step. All right, so we've seen this type of step in our Stille coupling. It's pretty much the same. So you have your both groups. They're now on the palladium 2. There is a nice propensity to form the carbon-carbon bond. That's a really strong bond. And palladium, going back to palladium 0, that's a pretty stable oxidation state of palladium. And so the reductive elimination could occur at this step. And you form your, in this case, your styrene product. And then you end up with your palladium 0 catalyst that now gets regenerated and now can go through another catalytic cycle. So now that we've seen each of these 4 steps separately, let's now combine them and show it as a catalytic cycle so we can kind of see how this process is actually pretty efficient. Okay, so we're going to draw a catalytic cycle, and we're going to start by just focusing on the fact that we are starting with our active catalyst, which is our PDL2. And we just said that the first step here is going to be an oxidative addition, where our vinyl iodide is going to oxidatively add to the palladium center. And so we can imagine the very first step in our catalytic cycle would be the vinyl iodide comes into the cycle, reacts with our palladium 0, and then we now form our palladium 2 complex. We said this palladium 2 complex, because we're dealing with an organoboron species, it's not really going to be able to do a transmetallation step at this particular stage. We need a little bit more oomph, and so we're going to do a displacement of our iodide with our ethoxide base. In this particular case, it is an ethoxide, but it could be any other alkoxide or hydroxide base in this particular step. And here's how we can think about our displacement, right? So as the sodium ethoxide comes into the catalytic cycle, sodium iodide leaves the catalytic cycle. And so we see that curved arrow showing what is coming in and what is leaving. And our product of the displacement step is our ethoxide latched on to the palladium, which has displaced the iodide. Then, now that we have our activated, if you will, palladium 2 species, now we can go through our transmetallation with our organoboron compound. So let's see how we can draw this catalytic cycle step. And here is how we are drawing our transmetallation. So as that phenyl substituted organoboron comes in, the ethoxy substituted organoboron leaves, right? So now we have this sort of transmetallation of our groups. The phenyl latches on to the palladium. It's still a palladium 2 species, right? We still have an X-type ligand over here, but now we have both groups that we're trying to couple to each other on the same palladium center, which means our last step is now our reductive elimination step is now more likely to occur to release our palladium 0 and to have that sort of return back into the catalytic cycle. And here is how we are drawing our reductive elimination. Our styrene leaves the catalytic cycle, so we can draw a curved arrow going outwards, and then another curved arrow going towards the palladium 0. So that's the catalytic cycle, at least the accepted catalytic cycle for our Suzuki Coupling reaction. So to wrap up this video, what I want to do is really think about these 2 organometallic reactions that we've learned so far, which is our Stille coupling and our Suzuki coupling, and do a little bit of a comparative analysis. What is different about them? What is similar? What's the advantage of one over the other? And in what context do we then choose which of the reactions to use? So first of all, the main difference between these 2 coupling reactions is based on what's the nature of the coupling reagent. So for our Suzuki, our coupling reagent is an organoboron compound, while the Stille coupling uses an organostannane or an organotin species for the reaction. With respect to our reagents we're using, our Suzuki reagents does introduce advantages. One, it is cheaper to acquire and buy organoboron compounds over organostannane. It also has lower toxicity, and so there's a little bit of a health and safety and environmental benefit of using our organoboron over an organostannane. So also, if we consider byproducts that are formed in both of these reactions, so when we look at our organoboron, our Suzuki reaction, what we end up forming is this boronate type byproduct versus a halogenated stannane product for our Stille coupling. From a synthetic point of view, the Suzuki coupling also, once again, gives us a little bit of an advantage here because it is easier to remove the boronate from the flask and separate it from the product you want than to remove the stannate species. Okay, and so that provides another additional advantage to using Suzuki over your Stille in chemical synthesis. Now let's consider the different kinds of bonds that can be formed for Suzuki versus Stille. Note that this is another way of asking what that substrate scope is for both of these reactions. So importantly, both the Suzuki and the Stille are really good at making carbon-carbon bonds with sp2 carbons. Okay, because that transmetallation, as we've talked about, is actually really good with sp2 type carbons like vinyl carbons or phenyl carbons. Those would all move or transmetallate from your coupling reagent to the palladium center. And so we can form arrow-arrow CC bonds, which is our first molecule we're seeing here. We can form arrow-vinyl CC bonds and vinyl-vinyl CC bonds pretty straightforwardly with both Suzuki and Stille, which makes both of them really compelling reagents or compelling synthetic strategies to use. For both of these synthesis strategies, we can also form sp3, sp2 carbon bonds, but specifically, it has to be the sp3 carbon of an allylic or benzylic group. So that sp3 carbon needs to be next to an sp2 carbon of some sorts. And so, but in these two cases, yes, Suzuki or Stille are fine. You can form both of these molecules using any of these reagents. The difference here really arises for where Suzuki, it has a little bit more, at least when it comes to substrate scope of your hydrocarbon, has a greater substrate scope. Because your Suzuki coupling can also transmetallate with fully saturated sp3 carbons. So we're looking at just alkyl chains. As you can do, especially, and the alkyl chain does need to be on the organoboron species or the organoboron compound. And so that can transmetallate because of that displacement step where the boron now has this additional oomph because it is bound to the oxygen, the ethoxyoxygen that is already bound to the palladium. That's such an activated boron that now really even the least transmetallating type reagents can still transmetallate. Okay, so we have a slight advantage again, where Suzuki is a little bit better, at least in terms of your substrate scope across your hydrocarbons. So at this point, you might be wondering, why should we ever use Stille coupling when Suzuki is just really good at a lot of things, right? But it's in modern chemical synthesis, you see Stille coupling still being used like pretty much across the board. You also see Suzuki coupling still being used in chemical synthesis in modern day. And so there must be a reason why Stille coupling is still good. So the last thing we're going to talk about is functional group tolerance. So both Suzuki and Stille do have similar functional group tolerance. Your organoboron in your Suzuki and your organostannane in your Stille, these groups are going to want to couple with your organohalides, right? So that's known. And so you can tend to have a bunch of other types of groups on your molecule and they pretty much remain intact, whether you have ketones, aldehydes, amides, esters, amines. These groups tend to be tolerant towards these conditions. But importantly, there is a major difference between your Stille and your Suzuki. Remember that your Suzuki requires the use of a strong base. So your sodium methoxide is what we use as an example, but it can be sodium hydroxide. All the other alkoxides could be used. And that creates a problem, especially when we're dealing with acidic protons in our reagents, in our reactants, right? And so traditional Suzuki coupling conditions are incompatible with acidic protons. And here's an example. Let's say one of your reagents included some kind of aldehyde somewhere on the molecule. Well, we know now from our previous videos that aldehydes in the presence of sodium methoxide are susceptible to reactions at the alpha position because our sodium methoxide is a base that can deprotonate the alpha position of our aldehyde. And you can now start forming these undesired aldol products, especially with your aldehydes, in your flask, right? So we've seen these types of reactions before, which now poses a problem for Suzuki reactions when you have these types of enolizable functional groups on your molecule. Right? You can think about this with esters, for example, amides, all kinds of these functional groups can form enolates, and therefore you can have side products if there's an acidic proton there. So you do have to be careful with some the functional group tolerance with Suzuki, where Stille, you don't have that kind of problem. So once again, this Suzuki is not all good. There are places and times when you're looking at your reactants where Stille coupling becomes more advantageous than Suzuki coupling. All right. So we have covered now Suzuki couplings. We now understand like kind of what the reagents we need to use for Suzuki couplings, the scope, and importantly, the base. Why that ethoxide, alkoxide, hydroxide base is incorporated in Suzuki coupling and how that helps with the reaction. We've outlined the catalytic cycle for Suzuki couplings, and then we finished with an comparative analysis of Suzuki versus Stille to figure out when would we want to use one over the other. Thank you so much for watching this video, and I will see you in class.